So next section is choosing a method, or you might call it a model, choosing the machine learning model. For a number of reasons, this is surprisingly unimportant, even though perhaps people's intuition would be that this is the most important thing. So here we've chosen R part 2. So R part 2 is a decision tree. I don't know who has or has not seen decision trees. This is a plot of the fitted decision tree for our example. So each of these bold words are one of the covariate columns in the data, and then it's got a less than the number or greater than the number that tells you sort of what the condition of that node of the decision tree is. So for your predictions, you sort of just push them down the tree. So you say, in my new data, is status less than 2? If the answer is yes, you go this way. If the answer is no, you go this way, blah, blah, blah. The numbers at the top are the predictions at that node. So once you don't go all the way down until there's sort of one data point per node normally. So this will be the mean of all the remaining training data points in sort of left at that point. So as you go down the tree, these kind of predictions would hopefully get sort of better. And the percentage is how much of the data, the training data, is in each of these sort of areas as well. So 28% of the data has thickness greater than less than 3. So that's kind of what the fitted model we made looks like. It does highlight some of the stuff I was discussing before. So you might be able to intuitively see that this is kind of very non-parametric. So until you fit the data, you won't know whether the relationship between thickness and survival is a straight line, or it might go sort of quite flat and then quite high, or it might go flat, sort of high in the middle and then back down again. You don't know that until you've fitted the model. So it's a very flexible model. It can fit kind of any shape that the data kind of tells it to. It implicitly has sort of deep interactions, but also it's quite, so you can interpret this a bit in some ways, but as this tree gets big, you can see that this would be very difficult to interpret. Just looking at this tree already, trying to understand what the relationship between thickness and survival time is quite difficult, because you've got these different kind of areas and there's interactions here. So any data that goes down this part of the tree never experiences this condition here. So it's sort of hard to interpret. And similarly, you won't know beforehand what the parameters are, if you see what I mean. So during model fitting, the model decided that this node should be relating to thickness, but a slightly different data set, and this same parameter here might relate to age instead. And so you don't even know what the parameters are, or you'll have a different set of parameters each time you run the model on slightly different data sets. So yeah, this is the decision tree that we did use. And decision trees on their own aren't particularly great, but they make up like a component of a bunch of other machine learning methods that we'll see in a little bit of detail later. So one of the reasons that I said that the choice of model isn't that important is because there's this theorem called no free lunch theorem. It's kind of proper pure maths, and I'm not good at maths to actually work through it myself. But sort of the things that come out of it is that there's no such thing as a universal best machine learning model. I think the way it's phrased in the theorem is like, for any given model, there is a conceivable data set where that model is the best model. So there's no way of knowing what the best model is. You can't like sit down and think about it for 2 hours and then be like, oh yes, random forest is the best model for this data set. So what you have to do is you have to try a few models and compare between them and see which does best. So in that sense, sort of really thinking carefully about your method isn't as important as having a robust workflow where you have baselines and compare some different models and see which model comes out as best. And then another reason why it's sort of less important than you might think is that there's an awful lot of just very good methods in machine learning. A lot of them end up looking quite similar, and because they're all quite good, a lot of them will make very similar predictions. And so some other things matter a lot more. So your cross-validation scheme matters more, your error metric matters more, which covariates you have often matters much more than the particular method you use. So a slightly better method versus a slightly worse method with a better covariate in. The worst method with a better covariate will often outperform the better method without the useful covariate. And try not to get too hung up on the method, and in particular, if you're kind of, one of the things you can get sucked into if you do like Kaggle competitions, if you've ever seen those, there's these like machine learning competitions, you can end up running like hundreds of models and they all end up the same. And it was just a waste of compute time. What you should have been doing was thinking more about your covariates or other things. So as long as you've got a good variety in your sort of suite of models, then that's often as good as you can do. So I'll go into some very brief details of a couple of the sort of groups of models you'll see. I don't want to get too hung up on them, partially because I don't think they're as important as you might think, and because there's hundreds of models, they've all got slightly different details. You can't learn all of them in detail, so it's just sort of getting an idea. So random forest, you can access it in caret by switching that method argument to RF or ranger. Ranger is like a more modern implementation of the same model. Instead of fitting one tree, like in our part 2 decision tree, you fit a lot of trees, maybe 1,000 trees, and take an average prediction over them. And the way you make each of those trees is you take a random bootstrap of the data. So this isn't bootstrapping for our performance like holdout data set. This is just a way of getting similar but different data sets. So it's fitting perhaps 1,000 trees to 1,000 bootstrap resamples of the data. So they're all slightly different. And for each node in the tree, so like this is a node, typically what a decision tree does is it checks all your covariates and chooses the best one to be the split for that node. In a random forest, for each node, we only consider a random subset of covariates. So M try. So you might say, okay, only try 10 different. So we've got 5 covariates in our data, I think. So you might say only try 3 randomly selected covariates at each node. Again, that makes the trees kind of quite different. It means that like a little bit of noise in some of the data doesn't end up like wrecking your whole model, and it sort of forces the model to look at the data in different ways from different angles, as it were. So it ends up being quite effective. Neural networks are, we hear about them a lot in the news. You'll hear them in Ezra's talk tomorrow. For a lot of sort of regression problems that I've worked on, neural networks haven't worked very well. But for some of these kind of very big problems and sort of image analyses, things like that, they're kind of now the state of the art, and they do work very well. They're made up with, you've got these kind of input nodes called, which are your covariates, and got an output node. So this will be, for a regression, this sort of the numbers that come out of this node will be numbers between -infinity and infinity. But if you're doing classification, the numbers that come out of here will be a probability of class A or class B, or you might have multiple output nodes if you're doing multi-label classification. Then the thing that really makes neural networks is they've got these hidden units in the middle. And so each line here is like a parameter, and you kind of times the covariate value by the parameter value, and that goes into this hidden unit. And then again, you take the sort of so sum across all the covariates into this hidden unit, and then again those sums go into the output with some more parameters here. So one way you can kind of think about this is that each of these little groups is kind of like a little GLM, perhaps a linear model or a sort of a logistic linear model, if they often end up being logistic in these hidden units, even if you're doing regression. So you've got kind of a bunch of little GLMs, and then you're kind of combining those little GLMs in different ways as well. So again, this is another sort of little GLM, and you're kind of just combining them all together. So if you want basic neural networks in caret, you can use method equals n net. And that doesn't take long to train. If you want to just play with it, that normally takes a few minutes or something. There's much better neural networks in there, but they quickly become a bit complicated. But this keras is the kind of one of the good methods around at the moment, and you can access it from caret quite easily. So the kind of, once you've kind of got this model structure built, you have to find these parameters. So you saw in that even quite simple picture that there's quite a lot of parameters. You have to find sort of good values for those parameters, and particularly there's lots of local optima. It's not an easy optimization problem. And one way we can think of that is that all those little sort of sub GLMs in the pictures, they're all actually identical in our example we had above. So you could just swap all the parameter values for one of those onto the other, and you'd have exactly the same model, but with different parameters, if that makes sense. So it's difficult for the model to know, sort of get out of local optima and things like that. So it's all about, this becomes these really complicated optimization problems. And then a lot of it's about deciding this architecture. So how many of those hidden units do you want? How many, you can have like whole extra layers of hidden units. When people talk about deep learning, that's what they mean, like lots of layers of hidden units. Is everything connected to everything else? So in our example, each of these covariates is connected to every hidden unit, but you don't have to do that. So convolutional neural networks are used for image analysis. What you end up saying is that like kind of 4 pixels next to each other in the image, they should all be connected to a hidden node and separately. And then there'll be another hidden node that's connected to the next set of 4 pixels, something like that. So what gets connected to what becomes important as well.